to make the project successfully. So as you know that the problem is like the problem statement over here. So that is we need to develop an intelligent traffic management system that will be using real-time intersection data to dynamically optimize signal timing, aiming to reduce vehicle congestion, wait times, and emissions compared to traditional fixed timer systems. So basically, our vision is to replace that rigid timer with a digital traffic conductor. So you can think of an experienced human police officer directing traffic at the chaotic intersection. So they are not using a stopwatch, right? So basically what they do is like they observe the flow, then they anticipate the needs and make the dynamic judgments according to the situation that is required to keep everyone moving. So our system will also do the same, but with the scalability and the precision of AI. So we will build an agent that learns through the millions of simulated experience and the intricate dance of urban traffic flow. So this will be a classic application for reinforcement learning. So the to bring this digital conductor to life, we would need a tightly integrated system of specialized modules. So the senses that would be the computer visions with YOLO. So that would be our system's eyes. That would be the cameras that is required. And basically, YOLO will be helping you with the videos that will be required, like how do we turn a video stream into a structured data. So we will be using a real-time object detection model, that is YOLO. So our choice is YOLO because it is you only look once, because it is already pre-trained and it's only chosen for one primary reason, that is speed. So it can process the video frames like incredibly fast, so which is very much critical for real-time decision making. So for every frame, the YOLO will give us a list of detected objects with bounding box. So that would be the coordinates of the rectangle around each car. And a class label would be, for example, in the traffic, YOLO will be using the rectangle boxes that would be the bounding box to identify that whether it is a car, a truck, or a bus. So that would be done by using a class label and a confidence score as well. So like how sure the model is. So the accuracy is provided over here. Then our code aggregates this information to answer the crucial question. So how many vehicles are currently in each lane? So this count becomes a primary input for our system's brain. So second is the deep Q network. So DQN agent. So this is the heart of the project. So reinforcement learning is about learning through trial and error. So we can use an analogy like imagine teaching an AI to play a video game like Pac-Man. So the state for Pac-Man would be like that state is the position of Pac-Man. So the ghost and the dots, but for our traffic agent, the state is the output of our vision systems. So that would be car in lane N, that is cars in lane like north, or cars in lane S, that is cars in lane south, or cars in lane E, that would be cars in lane east, and cars in lane W, that means cars in lane west. So, and we need to also see the time current light is green as well, so we need to put that as well. And the action, so the Pac-Man can move up, down, left, or right. So our agent has a simpler choice of actions, that is like either it can stay or change, but we need to stay on the current green light or change to the next phase. So that is also required. And there comes the reward part. So in Pac-Man, eating a dot is plus 10 points and getting caught by a ghost is minus 500 points. So for us, the reward must quantify our goals of reducing the congestion. So a great choice is the change in cumulative delay. So if an action reduces the total time all the cars have been waiting, then it would get a positive reward. But what if it makes the things worse? So then it will be getting a negative reward, that would be a penalty. So the deep Q network is a neural network that is trained to predict the Q value. That means Q value means the quality value for each possible action in a given state. So essentially, it learns to answer the question, if I am in this situation, that means this state, and I take this action, then what is the total future reward that can I expect to get it? So the agent will always choose the action with the highest predicted Q value. Q value means the quality value. So thus learning an optimal policy over millions of iterations. So third comes the virtual world. That would be the sumo simulation. So we would be needing to train a RL agent in the real world is impossible, right? So you can't have an AI causing 100 car pileup on its first day. So we need a very safe, fast, and reliable training ground. So sumo is the full form of sumo is simulation of urban mobility. Is that ground? So it is a hyper realistic microscopic traffic simulator. So we can exactly model our exact intersection. So we can also define the traffic flows and simulate rush hours, and also we can, even inject anomalies, like a car is being stalled, and if the car is stuck there for over 1 hour or something, if the car is not moving as well. So our agent's main agenda is to interact with this simulation, so running through decades of virtual traffic experience in just a few hours of real world training time. So the command centers, that would be, so that would be dashboards and APIs. So of course the system needs a way to communicate. So fast API provides the high performance nervous systems to connect everything. So the CV module sends the state data to the RL agent. So the agent sends its action commands to the Sumo simulator, that is a like, or any real world traffic light controller, and a React.js dashboard with D3.js for charting and Mapbox for visualization serves as our command center. So it is basically allowing us to monitor the agent's performance in real time, visualizing queue lengths, wait times, and what kind of the rewards that it is receiving as well. So this is very much crucial for debugging, evaluation, and demonstrating the system's effectiveness compared to a fixed timer baseline. So week one would be the foundation. So we are going to set up the core infrastructure, that would be ingesting video streams, fine tune YOLO on traffic footage, and build a faithful replica of the intersection in Sumo. So this week is about getting the sensory input and the environment right. So there here comes the week two part. So that means the integration. So over here we need to develop the DQ and agent in PyTorch or TensorFlow. So the key challenge this week is building the communication bridge. So that means the API that lets the agent read the state from Sumo and sends back an action, completing the learning loop. Then here comes the week three. So week three is intelligence and insight. So the agent is already in training, but we need to check whether it is learning well or not. So this week is about refining the reward function. That is basically very much critical part of any RL problem. So simultaneously, you will build the dashboard to visualize the key performance indicators that are KPIs like average wait time and etc. Then here comes the week four. So that comes the deployment prep. So stress the trained agent. So we need to check, does it handle certain traffic surges or does it recover from an accident scenario? This is about ensuring the robustness. So you will also finalize the documentation and containerize the application with Docker for easy deployment. So as you can see, the final deliverables that is required. So a trained reinforcement learning model capable of dynamically controlling traffic signals in a simulated environment, and a real-time computer vision module for accurate vehicle detection and counting from video streams, a suite of RESTful APIs connecting the vision model, that is the the RL agent, and the front-end dashboard, an interactive web dashboard visualizing live interaction traffic, queue lengths, and the agent's real-time performance and rewards, and a complete source code repository with setup instructions and documentation. So this will be the final deliverables required for project one. And this will be the tools and technologies that will be used to make the project one.
So, hi ma'am, my name is Saurabh. I have a question.
Yes.
So, where we should, so from where there is the data set we provide.
No, that is the challenge that you guys will be facing. So you need to either create the data set by yourself or you need to find it through websites.
I got a question as well. According to the training sessions, we are going to have three training sessions per week, right? So,
Yes.
would we be creating like our projects after the training sessions and implement what we learn on training sessions, or would we be given very basic stuff of it on the training session and have to do it everything else on our own?
So we will be just providing a brief walkthrough of the topics and the functions that will be required. But the main thing is that you guys will be needing to make the project on like by yourself itself. So this will be a challenge, I suppose.
Ma'am, when will be the training sessions? Like,
That will be informed by the support team. So now we will proceed to the project number two.
okay, ma'am. Just one more question. Like, previous to this session, only Git session has been done, no? GitHub or any other session has been done.
I'm not sure about that actually. So
Oh, okay, ma'am.
okay,
Thank
yeah.
you.
Thank you. So on the project number two is hyper local pest infestation forecaster. So over here, our vision is to give the farmers a superpower. So basically, as you can see, the problem statement is there. So we will create a predictive platform that acts like a hyper local weather forecast. So, but specifically for pest infestations. So instead of just showing the farmers where pests are today, we will show them a probability map of where pests are likely to spread in next 72 hours. So this enables a surgical proactive approach that is called precision agriculture. So a drone can also be sent to treat just a single hectare or even a specific row of crops. So the problem statement is that we need to create a predictive platform for farmers that will be forecasting the spatial spread of agricultural pests, enabling proactive, targeted interventions instead of broad reactive pesticide application. So we need to develop a precision agriculture tool that provides farmers with 24 to 72 hours forecast map of likely pest infestation spread. So this allows for targeted drone based spraying or manual intervention. So saving cost on pesticides and minimizing environmental impact. So the architecture, that would be the art of data fusion. So the accuracy of any forecast depends on the quality and variety of its data. So this system powers come from fusing multiple data sources together. So the evidence, so that is the multi-source data ingestion. So we are building a multi-layered view of the farm's health. So the view from the space, that would be satellites. So we will be using APIs to pull publicly available satellites imagery. So that is specifically looking at NDVI, that is normalized difference vegetation index. So healthy plants with lots of chlorophyll reflect a lot of near infrared light and absorb red light. So NDVI is a simple ratio of this reflection, giving us a powerful field wide health metric. So a sudden localized dip in NDVI is a red flag. So as you can see, the view from above, that is the drones. So when a red flag appears, a drone can be dispatched for a high resolution look. So this provides the ground truth to confirm if the plant stress is indeed from pests or not. And the invisible forces, that are the weather API. So a pest reproduction and migrations are heavily dependent on weather. So we will ingest forecasts for temperature, humidity, wind speed, and direction. A warm, humid front moving in from an already infested neighboring field is a massive predictor of speed. So here comes the diagnosis. So semantic segmentation with unit. So the raw drone image is just as pixels. So we will need to teach the machine to identify the specific visual signature of pest damage. So for this task, we will be using a unit specialized convolutional neural network architecture. It is called a unit because its architecture looks like the letter U. And it also has an encoder path that compresses the image to understand the context. So what is in the image, and a decoder path that expands it back to pinpoint the exact location. So the output is just not a box but a segmentation mask. So pixel perfect map highlighting only the damaged vegetation. So that is the con LSTM forecasting model. So this is our predictive engine. So we would need a model that understands how pattern change in both space and time. So this is what a con LSTM is designed for. So let's break it down. And LSTM, that is long short term memory network, is great at learning from sequences, like remembering the trend in temperature over the last week. And a CNN, that is convolutional neural network, is great at finding spatial patterns in images, like identifying the shape of an infestation. And and the con LSTM, that combines both of these. So each memory cell in the LSTM is a conventional layer. So this allows the model to take a look at the sequence of our data maps. That would be like NDVI map, pest damage map, weather map, and learn the complex spatio. That that means the temporal dynamics of how pest spreads under certain conditions. So And the farmer's interface. So the actionable dashboard. So the output of the conv LSTM is a sequence of future reach maps. So this must be presented to the farmer in a very simple, intuitive way. And a React based web app with Mapbox is perfect. So it will display the farmer's field, overlay the color coded risk forecast, and also feature a time slider to scrub through the 24-hour, 48-hour, and 72-hour predictions. So it will also calculate the key metrics like total average at high risk and send push notifications to the farmer's phone. So as you can see, the week one would be the data foundation. So the entire project hinges on reliable data. So this week is dedicated to building automated resilient pipelines using tools like Airflow to fetch satellite and weather data and then store it in a post GIS database. So which is basically optimized for geospatial queries. And week two is somewhat where we will be focusing on the computer vision component. So you will be needing a label of data set of drone images to train your unit model. So the goal is a model that can reliably segment new and unseen images. And the week three is this is the most ML heavy week. So you will prepare your time series, that is the sequence of maps, and train the on LSTM model. This involves significant experimentations with the model architectures and the hyperparameters as well. And week four is the last mile. So it is all about usability. So you need to finalize the forecasting API, polish the React dashboard to be more mobile responsive and intuitive, and implement the alerting system. So the goal is to deliver a tool that a farmer can use on their phone. So the tools and technologies, as stated, Sumo will be used, that is simulation of urban mobility, fast API, OpenCV will be also used. Then the final deliverables would be a trained reinforcement learning model capable of dynamically controlling. The pest ingestion, I think there is error in the documentation, but it is basically about the pest ingestion and things. So you need to develop an React based web app as well. So the dashboard is also needed. So the deliverables remains the same as stated for the first project. So the third project is the predictive maintenance for bike sharing. So over here, our vision is to equip every bike with a virtual check engine light. So, but one that warns it before the engine breaks down. So we will build a system that analyzes the telemetry from every single ride to predict the probability of specific component failures. So this will allow the operators to move to a predictive maintenance schedule. So instead of just sending the crews to fix broken bikes, we will send them to service bikes that are about to break. So it is a fundamental shift from operational chaos to data driven efficiency. So The architecture, that is the translating vibrations into predictions. So the key insight is here is that mechanical failures really happen instantly. So they leave subtle clues in the data leading up to the event. So our job is to find those clues. So the raw signal, so that is the ingesting the right telemetry. So as you know that each bike is a moving sensor package. So we will use Apache Kafka for a robust high throughput pipeline to ingest real-time streams from the bikes and IoT models. So the critical data points are GPS for locations, road beacon, and speed. An accelerometer, that is a three-axis sensor that measures vibrations. So this is our gold mine. Second is the art of interpretation, that is feature engineering. Raw accelerometer data is just a chaotic system of numbers. So it is useless to a machine learning model in its raw form. So the magic is in feature engineering, transforming this raw data into meaningful and descriptive features. So this is where the domain knowledge and signal processing come in. So we can create features like vibration frequency spectrum. So we can use a fast Fourier transform, that is FFT, on the accelerometer data. So a healthy bike might have a baseline vibration profile, and a developing issue like loose bearing or might introduce a new specific frequency spike, or the amplitude of that bike becomes a powerful feature. Ride roughness on smooth surfaces by cross referencing the bike's GPS with map data on road quality, and we can identify when a bike is vibrating excessively on a known smooth road, a clear sign of a potential tire or suspension issue that can indicate. And historical uses as well, like features like total kilometers ridden or number of rides since last maintenance, are also vital inputs. So the prognosis, that is multi-label classification with XGBoost. So with our rich set of engineered features, we can also train a predictive model. So the task is to predict the probability of failure for multiple components simultaneously. This is a multi-label classification process. So our model is XGBoost, a highly optimized implementation of gradient boosting. So it is famous for its performance on structured tabular data like our feature set. So we will train it on our historical data. So for every past maintenance ticket, that is for example bike hash 123 chain replaced, so then we will look at the features from the weeks leading up to that failure. The model learns the statistical patterns that can precede a specific component's breakdown. So the output for a bike might look like brake risk is at 92%, chain risk is at 45%, or tire risk is at 15%. So these are the basic components that will be required. And the action plan, that is the operations dashboard and route optimizer. So a list of probabilities is not enough. So we might need to turn the prediction into an operational plan. So we will build a React dashboard that is the central nervous system for the maintenance crew. It will display a prioritized list of bikes sorted by the highest risk score. So now we will go one step further. The dashboard will take the locations of top 15 bikes needing service and feed them into a routing engine. So this solves the vehicle routing problem, a more complex version of the traveling salesman problem, to generate the most time and fuel efficient route for the for the crew to follow on that specific day. So now we will see the week-wise data, that is from raw signals to an optimized workflow. So the week one would be the data plumbing. So we are gonna build the backbone, set up the Kafka stream for data ingestion, and the Postgre influx database for storing ride and time series data, and define the APIs for the bikes to send data to. Week two, we will be followed by finding the signal in the noise. So this is the core feature engineering week. So you will write Python scripts using libraries like Pandas, Cypher to process the raw telemetry into the meaningful features that will power your model. Week three is the crystal ball. So this involves splitting your historical data, training the model, and rigorously evaluating its performance using metrics like precision and recall for each label. So week 4 is something closing the loop. So building the final operational tool, develop the dashboard that displays the prioritized list, integrate a routing API like Mapbox optimization, and polish the user interface so it is easy for a maintenance worker to use it on a tablet in their van. So the technologies that will be used: Python, skitlearn, XGBoost, Pandas, Fast API, and for data streaming, PostgreSQL. And Influx will be using for time series data, Apache Kafka. Front end and visualization would be React.js, Mapbox or Leaflet can be also used, a routing API library. DevOps and journal that would be Docker and Git. So the deliverables are a predictive model that provides component specific failure probabilities, that is by like brakes, risk for every bike in the fleet, a real time pipeline to ingest and process right telemetry into meaningful features, and an operational web dashboard that displays a prioritized list of bikes requiring maintenance sorted by REST code, and a route visualization feature on the dashboard that suggests an optimal daily service route for the maintenance crew. And this is also required a complete source code repository with documentation for setting up and using the system. So, like across three different, different domains, so we have seen a powerful pattern change, like pattern emerge, that is sense, process, and act. So, sense the world using a diverse set of sensors, cameras, satellites, and accelerometers. Process that raw data, transforming it into the insight and foresight using the right machine learning model. Act on that intelligence by creating a tool that allows a human to make a better, faster, and more proactive decisions. So these projects are complex, but they are not magic. So they are the result of systematically breaking down a large problem into smaller, manageable modules and then connecting them with robust engineerings. So these are the technologies and patterns that we have discussed today are a toolkit, and I encourage you to start ma- like go through the project document and start working on the projects. So guys, please select your projects and start working on it slowly. Alisa, the review will be done. So post that there will be an email shared, and through that you guys can submit it, and we need to host it on GitHub. Then we can do that, and post the review, the projects can be submitted.
In the review we need to like explain the code and everything, no, what exactly we have implemented.
Yes, you can go through the deliverables part, as you can see. So for every project, a dashboard is also required. Complete source of code repository with setups and instructions and documentations. And this everything is required. You can go through the documents and it can be done. So like what all things that you have used, and there will be some questions in the review, and that's how it will be done.
Okay, okay. Thank you.
Hello, ma'am. I want to ask that for every group we have to submit the one project, or I want to say that individually you have to submit or group.
So actually, I am not sure if you guys have been segregated into groups or you can do individually. So that is something that needs to be confirmed by the admin itself. But as far as I know, you can do individually as well and in group as well. But I think you should get the confirmation from the admins once.
Okay, ma'am.
Yeah. So any more questions, or else we'll wrap up the session.
Ma'am, could you please scroll up for the project 3?
Project 3. Can you repeat your question, please, once again?
Yeah, yes, ma'am. Yes, ma'am. Project 3.
Ma'am, can you share the document on WhatsApp group?
Yes, you guys will be getting the documents soon.
It's already there in Google document.
Ha,
Google
yeah.
Sheet.
Yes, yes, yes. So
Ma'am, just for 2 minutes, can I check with anybody that whether they had session after GitHub, or this is like I missed any session? I want to check.
yes, yes, please.
Can you ask anybody to reply?
Okay,
I think last session is GitHub.
Okay, okay, fine, fine. Thank you.
okay, then we will wrap up the session. So, or somebody has asked when we need to submit the first project. So you can check in the project document, the week-wise plan is given, and for reviews, you guys will be informed when it is going to happen. But I will suggest that please start working on the projects from before end as well, and select your projects wisely.
So out of the three projects, we can choose any of the projects for the first month. It doesn't have to be sequentially, right?
You can choose any of the projects.
All right.
So, okay, then we'll be wrapping up the session now then.